Let's do a proof with this, a simpler proof. And I'll call this the transitivity of divisibility theorem. And this is real simple. Oh, it makes sense. It might look weird. And that is, well, I'll just write I'll just write it first. It means divisibility is transitive. It's one way to say it, but we haven't really defined what transitive means in this class yet. What transitive means for any kind of operation is that, like, for example, if A equals B and B equals C, that means that A equals C. Something like that, right? Or like if A is less than B and B is less than C, then A is less than C. Now, the reason this works is because equals and the less than sign are transitive, but not everything is transitive. It's kind of hard to think of one on top of my head because most things that we do, most things that, without using too advanced math, most things kind of end up being transitive, but it's not obvious that everything's transitive. Yeah. If you want a really complicated example, I can give you one after class. But anyway, so divisibility is transitive. What this means is, i.e., for any 3 integers, A, B, and C, if A divides B and B divides C, then A divides C. Right? This, I think, should kind of make sense. And like for example, let's do an example. For example, we could say that, yeah. For example, 3 divides 12 since 4 times 3 equals 12. And 12 divides 24 since 2 times 12 equals 24, right? And 4 and 2 notably are integers. That's why this is division. Or that's why that's why they are divisible. So yeah, so 3 divides 12 and 12 divides 24. And so now we can draw that, right? We can draw so this is a drawing that shows that 3 divides 12, because this says 12. So you can say that 3 divides 12, right? Because we can split it up into 4 pieces, each of length 3, right? 3 evenly goes into 12. We can also see that one, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16, 17, 18, 19, 20, 21, 22. Thanks, 24. You can also see that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1 to 9. Yeah. So we can see that 24 is divisible into two pieces of length 12. And then because we know that 3 divides 12, we can break each of these pieces of 12 into pieces of 3. Right, the point being that clearly, right, if 3 divides 12 and 12 divides 24, then we can figure out how to break 20, so we can figure out how to break 24 into pieces of 3, right? Benay asked, are we saying divides as being explicitly just a percent, oh, mod b equals 0? Yes, Benay, that'd be what you think about it. Exactly. And it's gonna come up, we have mods coming up in a few weeks. So good job. But yeah, so I think clearly this transitivity thing makes sense because if A divides B and B divides C, well then just think about how B goes into C and then put A into each of those B's and then you have it. In this exact example here, right, the way you mathematically do it is we have 4 times 3 equals 12 and 2 times 12 equals 24. So then 24 equals 2 times 12. And then 12 equals 4 times 3. This whole thing equals 2 times 4 times 3, which is 8 times 3. And 8's an integer, so 24 is an integer multiple of 3. All right, we're going nice and slow, I hope. So we're all getting it. The slow dance of divisibility. So yeah. So now I think we have enough information. Let's just write this formally and do a proof. So the formal way to say this is for all A and Z, and for all B and Z, and for all C and Z, A divides B and B divides C implies A divides C. Here's a question. Do I want an arrow going this way?
No, you do not.
No. What was that, Alex?
Well, you can actually just think about it with just one thing, right? If B divides C, C doesn't necessarily divide B, right? It's too big. It could be, for example.
Yeah, exactly. I mean, we might not even know that there is a B possible, in the sense that, like, we know if this happens, this will happen. That's why the arrow goes this way. That's what we're going to prove in a second. But if you have A divides C, for example, if you have, like, well, I guess it depends how you look at it. But anyway, we're just going to go one arrow for now, because going backwards, like, what even is B? Like, if you have A divides C, well, what even is B? I guess if there was a particular B that would have this happen, then it would work, but then it would have it happen. It's kind of circular. The point is we only want to go one arrow in this case. So let's prove it. Proof. Okie dokie. So to prove this, right, is a proof by direct method, because we're proving something about infinitely many things. We're proving something about all possible A, B's, and C's which make this work out. So this is a very big set of things. Method of exhaustion won't work. We're using direct proof. And what's the start to all of our direct proofs? We always say let. Well, what do we start out with, right? I mean, like, we have to start from somewhere. We have to start from something. We need something to play with, something to work with. So what do we start with?
A divides B and B divides C?
Yeah. So this is a universal statement, because we have the for alls here, about a conditional. And the way that you prove a universal conditional is so the way you prove a universal conditional is you need to prove that whenever you're in the domain and the hypothesis is true, the conclusion must follow. That's it. Whenever you're in the domain, the hypothesis is true, the conclusion must follow. So we start off by just having A, B, and C be any old particular, arbitrary but particular elements that are in our domain and satisfy the hypothesis. The important part is that they're arbitrary but particular, which again means that they're just like we're picking some out, but we can't assume they have any properties that not everything in the domain has. So let A, B, and C be arbitrary but particular integers such that A divides B and B divides C. So this is how you start every direct method proof, right? Just let these things be in your domain such that they satisfy the beginning. And remember, you might say like, well, how do you know A, B, and C are actually in a domain and do this? Well, you're just defining them to be that way because we don't care about anything that's not in the domain and doesn't satisfy the hypothesis because this statement is just a statement about things in the domain and have this hypothesis. So we're just going to define A, B, and C to be those because we don't care about anything else. Right now, we'll care later. But not that I don't care. You know what I mean. You know what I mean. One thing at a time is important. We compartmentalize our caring in this class. And right now we're dealing with this compartment. So, yeah. So we have this right here. And then what can we do with these guys, right? Like this isn't necessarily that useful by itself, like labeling them like this, but what do these actually mean under the hood?
There exists like in a, right, we just use the definition of divides, right? There exists an A such that there's a K, there exists a K such that A times K equals B, where K is in the integers.
Because A divides B, what that means is B is an integer multiple of A, right? So there must exist some integer K, must exist some K in the integers, such that B equals AK. I'll say similarly, since B divides C, there's a K and Z such that C equals BK. Now I made a mistake here on purpose. What's wrong with what I just wrote?
You should probably not have K for both A and, well, like B equals AK and C equals BK. Like
exactly.
They can't be the same particular K.
I very much enjoy your humbleness, Alex. But no need to say probably. You're totally right. And you know you're right. Right? Yeah. The problem is here we use K to mean two different things, and that's a big no-no. Never use variables. Use the same variable, I should say, to represent two different things. Right? This is important. This is huge. I'm going to triple circle this. Please don't do this. Right? This leads to a ton of errors. This is a big common source of errors. A lot of people do this because, like, like use the same variables over and over again. We use similar letters, but make sure that every time you use different things, use different variables. So here I should really say, like, there is, I'll call it T or something like that, and Z such that C equals bt. Because here, k represents the integer multiple you need to multiply a by to get b. T represents the integer multiple you need to multiply b by to get c. These represent two very different concepts. Nowhere here, nowhere from our domain and our hypothesis does it sort of specify that like a to b equals b to c, that k and t should be the same thing. Nowhere does it specify that, so we need to name them different things. Now, could k and t be the same depending on your a, b, and c? Yeah.
Absolutely.
It could be the same, right? For example, if a equaled 3, b equaled 6, and c equals 12, right? Your k here would be 2 to go to 3 to 6. Your 6 would be 2 to go to 6 to 12 as a multiplier, right? But the point is, even though they could be the same, they're not always going to be the same. So that's the whole thing about arbitrary but particular. These are arbitrary in the sense that we can't assume k and t are the same because we don't know they are based on for any old a, b, and c. And if they do happen to be the same, that's fine. It's okay if sometimes k would be the same thing as t. That's okay. So, don't make that mistake. Don't be me, right? I made this mistake right now, so you don't have to. Am I a martyr? Stop. Come on. But anyway, so we know that b equals ak and c equals bt. And then we have everything we need, right? We can just say thus. So we kind of work backwards here, right? We eventually want to get c as a multiple of a because we're trying to prove a divides c. So we want to get c as a multiple of a. So we're going to start with c and try to write it as something times a. So thus c equals ak by definition. By definition. And then ak, I'm sorry, sorry, b equals ak, c equals bt. By definition. But then b equals ak. By, this is what we call substitution, because we're substituting ak for b. There we go. And substitution you do with things that are equal, unlike like a sub-teacher, because no substitute teacher can be as great as me at discrete math. Oh, but anyway, yeah, so b, c equals bt, b equals ak, so you can substitute that there. And then we can do this little parentheses trick, right? AK times t is the same thing as a times kt. And this is by what's called associativity. And associativity, for those people that either never saw it or forgot it, that just means that like x times y times z always equals x times y times z. That's just, it works with plus too. Plus is also associative. S plus y plus z is the same thing as x plus y plus z. Yeah. That's very important. And then once we have that, that's kind of all we need. So now we've written C as A times KT, meaning that we've proven that C will divide, or A will divide C if what? We need one thing. We need to prove one last thing.
KT is in the integers because
right?
They're closed under multiplication.
Because, for example, you could always make something look like this. Like, for example, 17 equals 2 times 8.5. But this doesn't mean that 17 is divisible by 2. The reason being 8.5 is not an integer. So we need to be very careful to make sure that this is in fact an integer. We don't trick ourselves. We want to play ourselves, is the whole point. Yes, so we have A times KT. So let's note, since K and T are in Z, by definition, right? Because when we defined K, we said to be in Z. When we defined T, we said it's in Z. Since K and T are in Z by definition, KT is in Z since the integers are closed under multiplication. And that's one of those things we're allowed to assume. Therefore, so KT, this thing multiplied by A, is in fact an integer. Therefore, C, which equals AKT, is divisible by A by definition of divisibility. Square. We're done. That wasn't that hard, right? Any questions here?